Today is lecture 4, day 4 in Math 141. We still have just a tiny little bit of review material to cover, and then we'll go back to the back of the book in the appendix. Appendix B deals with linear functions, parabolas, conic sections in general. So we'll try to get through that today if possible. I think we were finishing up with logarithmic functions and how they're tied to exponential functions. So let's kind of wrap that up real quickly. If we have an exponential function, y equals 3 to the x, and we want its counterpart, its inverse, where we're switching x and y and then solving for y. Gosh, that sounds like a test 1 question, doesn't it? Find the inverse. So you would need to know to switch x and y, put a little star beside that as you write it down in your notes. Switch x and y and solve for y. And maybe even like give the domain of the original function and the domain of the inverse. Maybe we should talk about domains here too before we leave this. All right, inverse. Switching x and y. So y is in the exponent position. Whenever you want to solve for a letter, a variable that's in the exponent position, what should you do? What should we do? Logs. Some kind of logs. Now, probably your calculator doesn't work. I would imagine nobody has a base 3 logarithmic key. So we're probably stuck with 2 choices. Exponential or natural exponential, base E, natural logs, and base 10, common logs. So probably our calculators are going to work in those. So it doesn't really matter. I would say for this course, most of the time you're going to choose natural, exponential, and natural logarithmic functions. So if we were to take the natural log of both sides, or you can just think through it. You might choose to do that. What is y? Y is the power that you would raise 3 to get x. Maybe that'll work. In fact, let me write that down. Y is the power that you would raise 3 to get x. Let's take that approach this time. We could solve it the other way. And we should just show that they're equal. Y is, that would be y equals the power. What's another fancy mathematical word for power?
Exponent.
Exponent or logarithm. Power, logarithm, exponent, they all mean the same thing. So y is the power, y is the log, y equals log, that you would raise 3, so base is 3, to get x. So this equation and this equation are inverses of each other. Let's go back to this one. Natural log of 3 to the y would be, can't we bring that y out in front, right?
Yeah.
Why is that, by the way? That's not just some mathematical rule.
It's the rule of logs.
Okay, it is that, but there's another reason that you've dealt with a whole lot more than some memorized logarithmic rule. What is a logarithm? It's an exponent. What do you do when you have a power raised to a power? You multiply the exponents. Isn't that what we're doing? We're taking this power and we're bringing it out in front and multiplying it by this power. So that's what we have. We have a power raised to a power. That's the product of the powers. And if you solve for y, apparently that and that are equivalent. So one is in terms of natural logs, the other is in terms of base 3 logs, but they are equivalent. This would probably be better for a calculator. So you can use natural logs. This is probably not necessarily good for a calculator, but it is a little cleaner representation as far as base is 3 here, base is 3 here, Here y is the logarithm. Here y is 3 raised to the x, which is not the logarithm. So it's a little cleaner to see that they're inverses here. What's the domain here? Y equals 3 to the x. What can x be legally? Anything? Can you raise 3 to any power? 3 to the 0? 3 to the negative 5? 3 to the 7th? Okay. So the domain is all reals. Somebody brought this up the other day. Eric maybe brought this up the other day. If the range of the original function isn't real clear, we could go to the inverse and pick off the domain, right? Because that's how you, in fact, kind of see if they're inverses. The roles of domain and range have interchanged. I don't know. Let's try this first. What types of y values do you get when you raise 3 to x? And x can be any real number. Can you get a negative? Can you take 3 to a power and get a negative?
No.
No. Can you take 3 to a power and get 0? No. So 3 to a power is going to be something positive, right? So we want the range to be all reals, not 0, so I start right on the other side of 0, all the way out to positive infinity. Now, let's check and make sure that the domain here and the range here are, in fact, switched around from the original function. So what is y here? Y is the exponent. What can the exponents be? Real numbers, right? Those are the y values. Y's can be anything, real numbers. So the domain here is the range on the inverse. What about the range over here was non-negative values? Is that true about the domain here? We want to take the log of something. What type of numbers can you take the log of? Positive, right? We can't take the log of a negative number. If you enter that into your calculator's not going to like it. It's going to give you some kind of an error message. So on the function and its inverse, the domain and range are interchanged, which if you think about what an inverse is, that ought to make really good sense. We have completely interchanged the roles of x and y. What are x's and y's collectively? They're domains and ranges. So that should, in fact, be the case. All right, one last thing on inverses, and then we'll go to the appendix in the back of the book.
Sir,
Yes?
the range on the last one is from 0 to infinity, but I thought it couldn't be 0.
Remember let me bring this back. The y here is the logarithm. So a logarithm can be negative, right?
But not what you're taking the log of can't be negative.
That's correct. So let me give you an example. That wasn't good. I shouldn't have just said the same thing I said again because you had a question about it, obviously. So let's take that. The only thing is we're not going to be able to look this up on a calculator. But so let's say we had the log to the base 3 of some ridiculously small positive number. What power would you raise 3? And if you rewrote this statement, you'd say the base is 3, y is the exponent. You'd be thinking of a number that you could raise 3 to get some tiny little number. Wouldn't y really have to be pretty negative there? Is that okay?
Yeah.
If anybody else had the same question, y is clearly some negative number to solve that particular logarithmic equation or its counterpart, the exponential. So yeah, y can be anything. Large in magnitude, negative numbers, 0, and positive numbers as well. All right, sine of x. Let's say we want the inverse. And we will deal with this thing that is going to be the inverse of the sine, which I just gave you a big hint what we're going to call it. For lack of better terminology, this is kind of a little bit unfortunate, I think, in terminology, that if we solve this for y, let's translate it in the English language first, and then we'll translate it into a mathematical equation, which is the mathematical counterpart. What is y? Y is the angle that you're taking the sine of to get x. Is that correct? Mm-hmm. So y is still the angle that we're taking the sine of to get x. So the notation is that. Inverse sine. It does not mean sine to the negative first. Everybody okay with that? You've had a little bit of that before, I hope. So if this is our f of x, this is our f inverse. So inverse sine. Catherine.
So is it 1 over sine, so it would be cosine?
It is not.
It's
not neither one of those. Okay, that was actually a double negative, because 1 over sine, first of all, would not be cosine. That would be cosecant, right? And this is not cosecant.
Okay.
This is inverse sine. And this notation is confusing. It is. It's unfortunate that this notation was used, but this is an inverse sine but it's not the reciprocal of the sine. So if we were to plot points on both of these, you've probably graphed the sine function enough that you're kind of tired of it. So the sine value through its first two quadrants looks something like that. The inverse sine, if we're going to switch the roles of x and y, we can just take a few points, 0, 0. That's a tough one to flip, isn't it? That would be 0, 0 when it's flipped. Here's pi over 2, 1. So we want to graph 1 pi over 2. And here's pi 0, so we want to graph 0 pi. So there's an inverse sine. There's a sine graph. You should be able to draw in the line y equals x. And they should be mirror images of one another on either side of the line y equals x. What's the unfortunate thing about the red graph right here?
Not a function.
Not a function. So we have to kind of decide, we're going to make some choices with inverse sine. I'm sure you've heard of capital arc sine or capital inverse sine. When you work with capital inverse sine, you're going to work with this set right here, pi over 2 down to negative pi over 2. And when you restrict it in that fashion, then it does become a function. So when you punch in on your calculator, what's the inverse sine of 1/2? It's not going to give you a whole bunch of answers. It's going to give you one answer. So a lot of times when you take like a trig function, which is a function but not a one-to-one function, you take its inverse. This is because the original was not one-to-one, its inverse is not a function. So we have to restrict it, which for capital inverse sine, we will make a choice from negative pi over 2 to pi over 2. That's where we will pick our single solution. Now we will deal with inverse sine in some other ways. Let me see if I can do this real quickly because we need to get to the appendix to try to get back on track. Okay. Any questions or issues with that? So let's start with that. Y equals inverse sine of x. And let's say we want to make a diagram. And I'm probably the only one that wants to make a diagram right now, but let's say we want to make a diagram. What is y? Y is the angle whose sine is x. So I'm going to put this angle here at y. And if the sine of y is x, these two say the same thing. Y is the angle whose sine is x. If you take the sine of y, you're going to get x. Same thing exactly. Tell me how I can label this triangle so that the sine of y is x. What is the sine ratio?
Opposite over hypotenuse.
Opposite over hypotenuse. So I can label opposite x and hypotenuse 1, and we're in business. Is that correct?
Yeah.
Does that diagram say the same thing that this equation says? Y is the angle whose sine is x. Is that true on this diagram? And is that enough information to somehow find what the third side is?
Wait, is the hypotenuse, is that a 2?
That's a 1.
Oh.
Sorry. Doesn't the hypotenuse squared equal this leg squared plus this leg squared? Is that correct?
Yes.
So this leg ought to be hypotenuse squared minus leg squared square root. Is that correct? That will come into play later in this course. If we have an inverse trig or an inverse sine specifically, we can label the diagram, and that diagram will be helpful to us as we try to come back to basically eliminate y's and write our answer in terms of x only. All right. Appendix B in the back of the book. It starts on page, thought I wrote this down, maybe I didn't. I think A2 in the back of the book. Talks initially about the Cartesian coordinate plane. We've already been using that. Cartesian coordinate plane is the XY coordinate plane. Typically, the x-axis is horizontal, the y-axis is vertical. It doesn't have to be that way, but that's the way we're all used to. A7? Yes, there we go. Where did I get A2? Okay, maybe another edition of the book. A7, thank you. First of many mistakes today. You have to catch me on them, though. 4 quadrants of points, pretty much established by what is the relationship in that quadrant of all the x's and y's. First quadrant, positive x, positive y. Third quadrant, negative x, negative y. We know all that, so you can review that. Let's talk briefly about distance. Distance in the coordinate plane. If the 2 points are in the same horizontal line or the same vertical line, that's easy, but if they're not, let's say we're over here at x1, y1, and over here at x2, y2. Now everybody knows the distance formula. There's a reason why I want to start with this, is what we get to next, is if we want the distance between these 2 points, we can set up a right triangle by finding this point right here. What are the coordinates of that point that I have unlabeled at this point in time? Okay, x2, it has just as much x as this point. Does that sound good? And it has just as much y. It's up just as far as this point. So we've got a right triangle, and we've got a right triangle. We can use Pythagorean theorem. So what is this segment? what is the length of that segment, which is one of the legs of the right triangle?
y2
y2 minus
minus y1.
y1. We're assuming that y2 is above y1, so that difference would be positive. If it's not, we could take the absolute value. So I'll go ahead and do that, just to kind of validate the fact that it may or may not be above. Okay, what's the length of the other leg? Okay, they have the same y value, so it's not going to do us any good to mess with them. Okay, so it must be x2 minus x1. Again, just to make sure we get a positive, we'll take the absolute value. Pythagorean theorem, this leg squared plus the other leg squared equals this distance that we're looking for squared. Does it really matter now that I have absolute value? Now that we're squaring, it doesn't matter now. So this just happens to be that. So the order in which you subtract doesn't matter. You know that's true about the distance formula. And if we want to solve for d, that's our old friend, right? The distance formula. Difference of the x's squared plus difference of the y's squared equals the distance between the 2 points that we were handed to begin with. So what value is that? Well, there's a little bit of value in reviewing that, but probably more value in making the short leap then to circles. So what does distance have to do with circles or anything else that we're going to do today? Well, the definition of a circle is the set of points in a plane equidistant from a given point. Now, if we didn't have in a plane, what could this be? Could be a sphere, right? In fact, that is a sphere. If you had a single point in 3D or in space, and you had all the points that are equidistant from that point, they would comprise a sphere. We don't want a sphere, we want a plane figure. So set of points in a plane equidistant. So there's why we need distance. Equidistant from a given point. So here's our point. Let's call it, you'll probably like this, that sounds familiar. The center of the circle is HK. Doesn't have to be in the first quadrant, that's just where I happen to draw it. So we've got these points that comprise this circle. So I'm going to call them X, Y, because I want the X and the Y to kind of generically represent any and every point on the circle. And typically we refer to that distance as the radius, right? The distance from the center of the circle to any point on the circle. So let's use our distance formula. Distance from xy to hk equals r. Well, the distance from xy to hk, difference of the x's squared plus difference of the y's squared is equal to, in this case, r, right? The radius? Everybody agree? Simple distance formula problem all the way back to the definition of what a circle is. And we'll get a familiar friend here if we square both sides. Does that look familiar? Right? Good old standard form of the equation of a circle. May or may not be advantageous to us to know that when we start a problem, but eventually I think that'll come in handy if in fact it is a circle. So let's say that we know that the center, which was HK, is the point 1, negative 2, and the radius, let's say, is 5. Can we come up with the equation of that circle?
Yeah.
I would hope so. So x minus h is 1. Y minus k, y is, or the y value, the coordinate of the center, k is negative 2, and the radius squared. So that's pretty easy. If you're given it that way, that's a pretty easy problem. Is that circle in that form? Is that in standard form?
Yeah.
It kind of is. It's not like everything's spelled out, but what's h here? 0. K is 0. So the center is at the origin. Hopefully when you look at that, that's what you were thinking to begin with. And the radius is 4. Now, is that circle, pretty simple equation for a circle, is that circle a function?
No.
No. So what, if we want to deal with something that is in fact a function, we're going to have to specify so we've got this set of points. So let's come up with a way to represent this semicircle. How about the upper half circle? That's a function. So we'll take our equation, slide the x squared term to the other side, solve for y. Y is really plus or minus. So which one of those is the upper half circle? The positive one. So if we want the principal square root, then we're talking about the upper semicircle. And I'm not going to write this down because we're getting a little bit cluttered here, but the lower half circle is the negative of that square root. So both of them together, not a function. If you want to specify one, the upper half circle, the lower half circle, they are, in fact, functions, the semicircles. All right, one more circle problem. Okay, I'm just going to write that part down. Now, we're also going to go on today to conic sections that are not circles, time permitting. When I start writing the equation this way, how would you know this is a circle and not an ellipse? Pardon?
Isn't like x squared minus y squared or something like that?
Okay, well, though, yeah, if you see an x squared minus y squared, that's certainly not going to be a circle. What's that going to be? That's probably a good thing we're doing this.
Yeah, appropriate.
That would be a hyperbola, right, if you had the difference of the squared terms. Now, if we had a sum of squared terms, it could either be a circle, which, by the way, a circle is an ellipse, right, with the major and minor axes the same. But what if it's one of the kind of regular, kind of oblong-looking ellipses? How would its equation be different than x squared plus y squared?
Different denominators.
They would have different either denominators or they'd have different coefficients. If this were x squared plus 4y squared or 16x squared plus 25y squared, that would trigger in your mind that's not a circle, that's something else. But the fact that they have the same coefficients and they are added, that's a circle. I have asked a question like this on a test before. Identify it. Well, we already identified it, that it's a circle. You'll probably know every question on the first test by the time we get there because I just tell you what I've asked before, and math hasn't changed over the summer a whole lot. So you'll have a pretty good idea what kind of questions. All right, somebody attack this. What do? You've seen it before, probably.
And you group similar.
Okay. Group things together. Let's get all the x terms together. Does that sound like good advice? As long as Eric says it, we're going to use it, right? Because he's been right so far, so we like what Eric's saying, so whatever he says, we're going to do. I'm going to leave some space. Is that okay? Would you like to leave some space? And if so, why?
Because you have to square.
Okay, we're going to complete the square. So now I'm going to go to the y terms. And what do you want to do with the 13 that's on the left side? Let's move it to the other side so it would show up as a.
How to do this?
Okay, that is the same equation with some different groupings. All right? With regard to the x's, what do we need to do?
Take out an X.
Take half of 4.
Take half of -4, square it,
Yeah.
and add it
To both sides.
to both sides. Good. So we'll add 4 to both sides. It is an equation, so whatever we do left side, we better also do to the right side. Now, that completes the square. Why do we want to complete the square?
So we can get this.
So we can put it in that other form, right? That standard form. So this now becomes a perfect square. That's what completing the square means. All right, what completes the square in y?
Take that one again.
Good. Half of that. Now, that's half if the lead coefficient is 1, right? Which it is, 1y squared. Half of the coefficient of the middle term is 5, squared is 25.
Okay, now I know.
Add that to both sides. That makes this a perfect square. And on the right side, we just kind of put our numbers together. What, 16?
Yeah.
So there's our standard form version of this general form start. Center is what?
2 -5.
2, -5, and radius is 4. So if it's not in the form that we want it in, kind of rearrange some things, complete squares, make sure you add things to both sides, and get it in the form that you want it. Is that all right? Any questions or issues with that? Yes?
Wait, so can you just go over how to complete the square? You want to...
Okay, where'd that 4 come from?
Yeah.
Okay, so you want to look at this coefficient
Okay.
of the linear term, the middle, what's going to be the middle term. So the coefficient is -4. Half of that is -2. Squared is 4. So you take half of the coefficient of what will be the middle term, half of the positive 10 is 5. Squared is 25.
How would you do one if the coefficient of the leading term wasn't 1?
Okay, good question. Is that question answered? First of all, okay. All right, let's say we had 3y squared plus 8y, and we want to complete the square. This is not going to be pretty. So the first thing we would do would be to divide through by 3. So we have 3, let me start again, okay? Let me start again with an equation. That'll be easier because we're going to have to do the same thing to both sides. So I kind of want to divide by 3, but I can't divide by 3 unless I divide both sides by 3. Let's factor out a 3. Probably be a better approach to what I did before. If I want to factor out a 3, then that's going to be y squared. This is where it kind of gets a little ugly. What if I factor a 3 out of there?
8 over 3.
8 over 3. Factoring a 3 out means basically dividing by it, right? Now, I haven't done anything to the left side. I haven't added anything or subtracted anything. I've just kind of made it look a little different. Now the task would be to complete the square inside parentheses. So we'd take half of 8/3, which is 4/3. Squared is
16 over 9.
16 over 9. All right, the question is, did I just add 16 over 9 to this equation, to the left side? No, I added 3 times 16 over 9. So I have to add 3 times 16 over 9 to this side. So it does get a little uglier when the lead coefficient is not 1. We have to make it 1, which means factoring stuff out and then kind of keeping track. So 3 times 16/9 got added here. We have to add that here. So if it's not 1, we have to make it 1, normally by factoring things out. All right, let's switch horses here to lines. Linear equations, which is also a topic in this Appendix B in the back of the book. This term is a critical term for this course, slope. Lines have slope. The nice thing about lines is their slope is fixed. It's always 2/3 or it's always -3. Never changes. Curves have variable slope, but we're going to get to that point where we talk about slopes of curves, but right now slope of a line. The probably first description or definition that you learned for slope was rise over run. That's still a very, very good description or definition. Rise, this kind of rhymes, by the way, if you ever forget what goes in the numerator. Rise and wise, they kind of rhyme a little bit there. So they go in the top. And run, I wish we had some kind of little something there to remember, but we don't. But if you know the y's go in the numerator, then there's only one place left to put the x's, so they go in the other place. So if we know the slope of a line is 2, we know a little something about that line. All kinds of lines, by the way, have the slope 2, but they all do what? What do they all have in common if they all have a slope of 2? They're all increasing as you view them from left to right, and they all have rise over run as a 2-to-1 ratio, right? What if a slope is 0? I don't know if we've talked about that in here or not. I think we have. What makes a fraction 0? 0 on top, which means they don't have any rise. Isn't that true about lines that have slope 0? They don't rise at all they do is run. So this is horizontal. What if the slope is -1/3? Well, we have this visual image that it kind of falls or decreases from left to right, and we in fact know the ratio. It falls 1 unit for every 3 units that it rises. So it's a little flatter, right? This is steeper. This is a little flatter in a sense that it's closer to horizontal. Point slope version of a linear equation. If you know the definition of slope, I'll slightly change it. This would be, by the way, when you see a subscripted letter, y sub 2, y sub 1, that means we know them. Some specific y, some specific x. So I'll use the same format, but I'll leave one of them kind of open, that it's going to describe all y's and all x's on the line. But that's pretty much the definition of slope. And if you'll take that definition of slope and cross multiply, you get our old friend there, which is the point slope version of the equation. If you plug in a specific x and a specific y, and you know the slope, then you plug them in there. And in fact, if you get to this point on problems in this class, I'll let you stop at that point. You don't need to simplify them any further because I know that you know what you're doing. So if you get to that point in this class, if I ask you to find the equation of a line, just stop when you get it here. Slope intercept. That's a pretty easy version to graph from, is slope-intercept. Well, if you know the intercept is some point 0, b, and you know the slope, then you can use that point slope that we just had, y minus the known y equals slope times x minus the known x. The known y is b. The known x is 0. Y minus b equals mx. It's starting to look familiar. Take the b to the other side. So there's our old friend, the slope-intercept. So here the slope is m, and the y-intercept is b. Whatever sign it carries in front of it, we need to pick off. Also, it could be negative. All right. Let me ask you to do some work. Slope is 2/3, and the line contains the point 1, 2. Take about 30 seconds, come up with the equation for that line. Go ahead and get it in this form. Let me ask you to do this for right now. So go ahead and multiply stuff out. AX plus BY plus C equals 0. Okay, Nicole, tell me what to do. I don't have a clue. You're just going to tell me what to do here.
Well, you have to put it in point slope form.
Okay? I don't know
since
what that
we
is.
have a point. So you're going to do y1 or y minus 2 equals your slope, which is 2/3, x minus 1.
Okay, everybody agree? Good start? All right, now what?
Well, what I always do first is multiply through the slope. So your left side would still be y minus 2. And your right side would be 2/3 x minus 2/3.
How many of you did that? Okay, several of you didn't do that because I don't see everybody's hand up. If you didn't do that, what did you do next? How many of you love working with fractions in here? Love fractions. You do? You're okay with it? I don't love working with fractions. Let's get rid of fractions.
Yeah, I hate
So I don't know much, but I know I want to get rid of fractions. Okay, how can I get rid of fractions at this point in time?
Multiply by 3.
Multiply both sides by 3. Let's do that. Who did that? Who got rid of fractions? Okay, a lot of you did. All right, so that takes care of that 3, right? We're stuck with the 3 on the left side, but that's an integer. I can deal with integers. And then we've got this 2 that needs to be distributed. Not a whole lot different than what Nicole came up with on a later step. Okay, now what?
Add the 6th, the right side.
Okay, you want to move everything right? So what's the end result going to be?
2x plus 4.
Oh, okay, so you're adding 6,
Yeah.
adding 6.
And divide by 3 on both sides.
Okay, well, let's go for this form, which means that we would what?
Just move it over.
Subtract 3y?
Mm-hmm.
At least it's on vibrate. That's good. Hopefully that's not mine. I think I turned mine off. All right, everybody agree that that's a legitimate form, kind of this form?
Yeah.
Now, she also said, let's divide by 3, which kind of takes care of what I tried to do earlier was get rid of fractions. It reinstitutes fractions. That's fine. At least we can see that the slope is the correct thing, right? 2/3 was the slope, and in fact we have 2/3 where it should be. We weren't given the y-intercept, but now we know the y-intercept. So it kind of depends on the form that you want to have your answer in. But looks like everybody did that correctly. Somebody's persistent there. Midpoint. If you had 2 points in a plane, actually, let's do this problem. 2 points in a plane, let's say 4, 5, and 2, -3. I want to find the equation of the perpendicular bisector. Gosh, there's a good old geometry term. Perpendicular bisector. So 4, 5 is somewhere up here. 2, -3 is somewhere down here. It's a sketch. It doesn't matter that it's not all that accurate. So here is the line segment that connects those 2 points. We want the equation of the perpendicular bisector. All right, give me some hints here.
First, you got to find the midpoint.
Okay, we need to find the midpoint. So anybody remember that one? How do you find them?
X1 plus X2 divided by 2.
Good. How did you remember that? Just
Yeah, just remember
It's like the average.
it's kind of average, isn't it? If you add 2 things and take half, that's the average. So if you didn't remember that, then just remember it's the average of the x's, comma, average of the y's. So in our case, the midpoint, 4 plus 2, half of that. 5 plus -3, half of that. So our midpoint is what point?
31.
3, 1. So we know our perpendicular bisector goes through the point 3, 1. Give me some more information here. Keep me going on this.
You have to find the slope, and then the perpendicular slope would be the opposite.
Inverse.
Keep going. Oh, it sounds good. Right. Negative reciprocal, right? So let's find the slope of the given line segment. So difference of y's, 5 minus -3.
Does it really matter which ones you subtract or?
No. Order is irrelevant as long as you're consistent.
All right.
So if I start here with 5 minus -3, I've got to come back here and start with 4. So 4 minus 2. So what do we get? 8 over 2. The slope of the given line segment is 4. What's the slope of the perpendicular? Negative 1/4. All right, so everybody agree that this is sufficient information? We now know the slope of the line. We now know it goes through this point. Everybody feel confident you can take it from there. Is that all right? We just did that?
Yeah.
All right, so that should finish us with the lines part. We do need tomorrow to dig into the conic section part. Might be helpful for you to read through that. You may have done parabolas, ellipses, and hyperbolas before, but it would allow us to move probably just a little bit quicker if you've looked at that in the appendix before tomorrow. So you had a question on WebAssign. I guess we'll have to table that. We'll start class with that tomorrow. See you tomorrow.